Okay, this is 2.8, more examples on 2.8. So here we go on them. And it's only one page. So hopefully it won't be too bad. There are related rate problems. Some of my favorite related rate problems, in fact. Draining a water heater that has the shape of a right cylindrical tank with a radius of 1 foot and a height of 4 feet is being drained. How fast is the water draining out of the tank in feet cubed per minute if the water level is dropping at 6 inches per minute? And so I notice I have a unit mismatch here going along. They were talking about feet. They want the answer in feet. And then they said here that we have something happening in inches per minute. Now, I also noticed that the unit they wanted was minute. I've told my friend, go buy us a lottery ticket. I'm really tired and I want to call in sick tomorrow. And so if we win the lottery, and so he's texting me and making plans. We're making plans for the winning of the lottery. All the things we're going to do. I'm going to set up a scholarship fund for students. That's one of the things I'm going to do. And I'm also going to go to Florida tomorrow. And so, okay, so I got to draw the water tank because I haven't won yet. So they said it was a cylinder. To me, a cylinder is like a pop can. So there, I've drawn it. And there's some water in this tank, and I'm going to draw the water in the tank. And so this is where the water is. Water, and I'm spelling water with an H. Oh my goodness gracious. And the water is being drained out here. There the water is coming out. Okay. And so so that's kind of what we have. So as the water drains out, the level of the water should go down. They're not putting water back in. And so that's kind of what we have going on here. I was talking about this until I got a text about winning the lottery. And I was saying that we needed to turn this into feet. Everything needs to be in feet. So this is really a half a foot. 6 inches is half a foot. So it was nice of them to have it such a nice value. So this is 0.5 feet per minute is what that is right there. So let's write all the things that they kind of gave us out in this problem. They said that a water heater that has the shape of has a radius of 1 foot. So I'm going to put the radius of here at 1 foot. Now I want you to notice that is the radius of the cylinder, and that's the radius of the water. And as the water drains out, the radius of the water doesn't change. So as the water level gets lower, so the water drained down and the water level got lower, right? So it's not here anymore, and the radius is still 1 foot. And it gets a little lower, and the radius of the water is still 1 foot. But I want you to notice that the height of the water is changing. And so as time goes on, from the start of the problem to the end of the problem, as the water's draining out, the radius of the water remains 1 foot. But the height of the water keeps getting lower and lower. And in fact, they said it's dropping at half a foot per minute is what it is. Okay. So R is a constant here, and let's see what else that it said. The water heater itself is 4 feet. So this is 4 feet is the height of this water heater, and but that's not the height of the water, and so because the water is but the water heater stays 4 feet. It doesn't change. As we drain water out, the water heater doesn't get smaller. Just the level of the water does. How fast is the water draining out of the tank in feet cubed per minute? And so this water draining out is actually a volume, and they kind of are telling us the volume feet cubed is volume per minute. So they're wanting to know the rate that the volume is changing per minute as that water drains out. Okay, so that's what they're wanting to know. So they're wanting me to find dV dt. Notice the units. Feet cubed, that's volume. So the change in volume per time dt, and time is in minutes. So they want me to find dV dt when, and then they said the water level is dropping at 0.05 feet per minute. And so that is the height of the water. And so because this cylinder, this is called the radius and this is called the height. And so this is 1 dH dt. Notice the units, feet per minute. So dH dt, H is in feet, and dt is a unit of time. And so this is 0.05 feet per minute. Now the water level is going down, and the water, they want to know how fast is the water draining out. I think it's okay for me to have my volume be a positive value on this. Sometimes you want a negative value to show that it's draining out, but since I say it's draining out at this amount, I think it's okay for me to have it be positive. So my volume equals, because this is a cylinder, pi r squared h. And the volume of the water is changing. Pi is a constant. The radius is a constant of the water from the beginning of the problem to the end of the problem. And the height of the water is changing. So it is okay for me to go put in 1 foot for the radius. So the volume, because it's constant, equals pi times 1 foot squared times h. And now 1 foot squared, so this is going to be volume equals, this would be pi times 1, which is pi, and then I'm going to say h, and then I'm just going to put over here that the units right now are feet squared. That's the units I have on this side, because I want to show you that my units turn out to be the same, but I'm trying to ignore them. So now I'm going to find the derivative. The reason I couldn't put in the value for h is because h is not constant. H is changing. And so, and when I find the derivative with respect to time, this will be dV dt equals pi is a constant, dH dt. And they said that dH dt was equal to 0.5 feet per minute. So dV dt equals pi, remember the units on this were feet squared. dH dt is 0.5 feet per minute. And we already had the units from feet squared going, that came from the radius, right? And so when we put these together, this is pi times 0.5. 0.5 is half, so this is pi over 2. And this is feet cubed per minute. And that's what dV dt is. And you notice I put the answer down here. And so it's draining out at this rate. Okay, and so the next problem is about a it's draining another tank. An inverted conical water tank with a height of 12 feet and a radius of 6 feet is drained through a hole in the vertex at a rate of 2 feet cubed per second. What is the rate of the water depth? What is the rate of change of the water depth when the water depth is 3 feet? Hint, use similar triangles. So I'm going to give a whirl to this. Where you see these conical shaped tanks is in microbreweries. So the first time I ever saw one was in Boston at Sam Adams, going on on the tour of their brewery. But since then, I've seen them in lots of microbreweries. So they're kind of the thing. Okay, so I've drawn one, and I probably don't have it to scale, and I don't care. But it is 12 feet in height. Actually, it's pretty good. The water's going to come dripping out here. And so this is 12 feet. And then this radius right here is given to be 6 feet. And so that's kind of what we have going. I want to draw this 12 feet over here, and I wish I would have. So right here is 12 feet. The reason is I want to show you where the triangle is. And so I drew it over here, and then you can't see the triangle. Here's the triangle. And it's a right triangle right there. Do you see the triangle? Okay. Now, there's water in this this conical thing. And as the water drains out, I want you to notice that the height of the water is changing, and also the radius of the water is changing. So when when the water is at the very top, then there's 6 feet radius of water. But as it drains out, it gets lower and lower until down here it's just barely any. The radius might even be, not even 0.1 feet down there. At some point, it's going to be 0, is what it's going to be. Okay, so here I'm just going to draw where the water is, and I'm going to use the variable R, and that's going to represent, so right here is the water level. So there's my water, and this is going to be, I'm going to use the variable R for the radius of the water, and I'm going to use H for the height of the water is what I'm going to use. And then I have these similar triangles that are right here on that right cone. And I know that R is to H as 6 feet is to 12 feet. And how that's going to help me is that I'm going to solve this for the variable. I'm going to write up my formula for a cone. Volume equals, is it pi over 3 for a cone? Pi over 3 radius squared times height. I have to look that up on my phone because I am right now not remembering that formula for a cone. I'll have to memorize it. I think I have it right. Volume of a cone. Yeah, it is. This is right. They don't have it the way I would like to have it written, but it is the same. So I'm all good. And so V is changing. The volume of the water is changing, right? That's the volume of the water, and that's changing. R is changing, and H is changing. And so when I take the derivative, I'll have dV dt, dr dt, and dH dt. But when I read carefully to what I have been given, right here it says a hole in the vertex, the water is being drained out at 2 feet cubed per second. So look at the units on that. That's dV dt. And this is 2 feet cubed per second. Right? Okay. And then it asks, what is the rate of change of the water depth? Now I called it height. And so they're asking me to find dH dt. Now, they didn't tell us that it is going to be, like on this other one, they said the water's draining out, the height is going down, and they want to know how fast is the water going out. On this one here, they want to know at what rate is the water changing. And so if the water is, I can see that the water is going down, so that's going to be negative, right? And but they want to know the rate that it's changing, not the rate that it's going down. If they said, what is the rate that it's going down, then I'd have it be positive. But when they say, what's the rate that it's changing, then I would say that's going to be a negative value. So my dV dt is a negative value, and I know that'll make my dH dt be a negative value. Now, the reason I wanted to show you that is I don't want R in this equation because I know what dV dt is. I know what I want to find dH dt, but I don't care about dr dt. But when I take the derivative of this, because all of these things are changing, I will have an dr dt. And here I don't know what it's equal to, so I won't be able to find dH dt because I won't know what dr dt is. And so what I'm going to do is I'm going to use this equation right here, and so this becomes R over H equals half, which becomes R equals 1/2 H. And then I'm going to plug that in for R. And then I won't have any R's in my equation. Your textbook, every single problem that they have in there, that's the trick on these cones, is that you find out what R is and replace it. And I wish that they didn't have it be like that every single time, but that's how they have it. I was looking at some problems in some other books, and they wanted you to find dr dt, and so they would give you things of getting rid of H. But this one, anyway, so just so you know, that's what they do. So I haven't taken a derivative yet, but I'm gonna clean this up just a little bit. This is pi over 3, and then this would be 1/2, so squared would be 1/4, and then H squared times H, and then and so the volume will equal pi over 12 H cubed. And then now I am going to take the derivative. And so now I'm going to find the derivative with respect to time. With respect to time. I had to fit time on there. With respect to time. And so when I do, the derivative of V is dV dt. And pi over 12 is a constant. The derivative of H is 3H squared dH dt. Remember that I'm wanting to find what H is. And they had told me, so they said find dH dt, and I forgot to write down when H equals 3 feet. So now that I found the derivative, I can plug everything in. So this is negative 2 feet cubed per second equals pi over 12 times 3 feet, quantity squared, and then dH dt. So when the dust clears here, this is, well, the 3 and the 12 cancel with one another, and 3 squared is 9. And so let's see here. This would be 9 pi, the 3 here over 4. And this is feet squared dH dt. Did I make a mistake there? Make sure, check. The 3 and the 12 canceled and made a 4, and 3 squared was 9, so 9 pi. And then minus 2 feet cubed per second. And I'm going to divide. I'm going to do it in 2 steps because I'm so tired. Do y'all agree that feet cubed divided by feet squared, I'll just do the units first, are feet per second, because over here feet cubed divided by feet squared will make feet, and then feet per second. Okay, so and then I'm going to multiply by 4, so that's going to make negative 8, and this is going to be, and then I'm going to divide by, I multiplied by 4 to get rid of the 4, negative 8, and then I'm going to divide by 9 pi, and then I did the units, right? Feet cubed divided by feet squared are feet per second, equals dH dt. So the rate of change of the water level is this negative value. If I wanted to say the water, if I wanted to say the height of the water was decreasing, I could then say a positive value at 8 over 9 pi feet per second. Anyway, we did a lovely job on that one. It was beautiful. It barely fit in the spot. You might have to, I might have to say to myself, give more room next semester. Okay, video number 2 made, and this one was truly 2.8.